The suggestion then was to take a look at task 17 about shielding. So as usual, I will try to copy this if my computer allows me to do so. This now works. Okay, and paste it into my drawing program, which is here. And then we can have a look at this task and see, okay, it's about a computer case consisting of steel, and the dimensions are given, so it's like a usual larger kind of computer case, and the steel has a certain wall thickness of 0.6 millimeter. Okay, and so what we should do is calculate the expected shielding efficiency of the single wall at 500 megahertz. If the field is a far field, or if the source is a far field source, and we can do this exactly and approximately. And maybe we start with this task first and then have a look at the other tasks. So for subtask A, I will use black. And the question is, how would you do this? What would you suggest for the solution? Or what would be the corresponding theory that we could use to calculate shielding efficiencies or shielding effectiveness? So if we switch back to our lecture slides and go for shielding. So, and we had this shielding theory of Schelkunoff, and discussed this, that we have this external wave, and then we have reflection and absorption and transmission and so on through the shield. And we, after all the derivation and all the formulas, came up with some formula that would allow us for some exact shielding efficiency calculation. So this would be the exact formula, and then we had some approximative formulas where the shielding consists of reflection, absorption, and some correction term for multiple reflections. And so we can maybe rely on what we already did in one of the tasks before. That is still open here. That was the solution of task 16, I think. I think this was the one that we developed in one of the last exercises where we had the copper and aluminum and stuff. And so this was the exact solution that I can more or less copy here. So maybe I will take the whole solution and copy it into a new script, and then we can see how we can combine this with our calculation here. So we have, as the wall material is steel, so what properties would we need to know from the steel? We need to have kappa, we need to have the conductivity, of steel or iron, and we would need to have the permeability of steel, also at this particular frequency. So now we could, I don't know, go to the Wikipedia and search for steel or search for iron. Do I have this here? No, this is Wiktionary. This is the English Wikipedia. And then on this page, just look for conductivity. And This is thermal conductivity, this is electrical resistivity. So if we take this and maybe paste it here. Now the question is, how can we convert this into conductivity? Resistivity is what I would call, for example, ρ, and conductivity should be 1 over this resistivity. And so if we go to our Octave script here and insert the value of resistivity of steel, which is 69.1, and then nano-ohm per, or no, nano-ohm multiplied with meter. So nano is 10 to the power of -9. And so if we just from this calculate kappa of steel, it should be 1 over this, 1 over rho of steel. And if I calculate this, then we get 1.04 times 10 to the power of 7. And yeah, this also somehow makes sense, because if you remember in the other exercise task about shielding, in one of these subtasks somewhere, for the task 16, we also used a steel wall, and for the steel there, here we used 9.3 times 10 to the power of 6, and now here we got something like 10.4 to the power of 6, which is in the same range or same order of magnitude. So of course it would depend on what type of steel or iron do you have exactly. So here we get from our Wikipedia value, we get 10.4 times 10 to the power of 6 Siemens per meter. Okay, so we can go back to Wikipedia and maybe check for permeability, and permeability is unfortunately not given on this website. So maybe then we can just search there for permeability in electromagnetism, and let's see if there is somewhere a table values for some common materials. And here we have iron, and there is some value given here which is super high, 200,000, but this is pure iron, but there is no frequency given. And yeah, so if you can see, if the iron is not that pure, it's much less. If we have, I don't know, cobalt, iron, whatever this is, it's much less. If we have electrical steel, ferritic steel, I don't know what this is. And so different types of steels that all have values in the range of a couple of hundred to some thousands, but no frequency is given. And I would say that, so for the other materials you can see here, it's always just in the kilohertz to lower megahertz range. Just some iron powder compound, there you get something up to the 100 megahertz range. So I would say if we have this at 500 megahertz, there is no permeability anymore that is much larger than the permeability of air or vacuum or so on. I don't know if this is written here somewhere in this article. So this is some gyromagnetic ratio, and this is this maximum frequency. So usually permeability is only something that you have, let's say, at lower frequencies. And at higher frequencies, we can say this is approximately 1, at least at this 500 megahertz. So there will be no useful permeability in this case. Okay, so with this we can go back to our calculation here. Maybe I will save this as task 17 now. And so we have some conductivity, the thing of aluminum and copper I can delete. Then our relative conductivity that we need later on will be the one divided by the copper. But for this, of course, I need to have the value of copper at first. This is epsilon, this is mu, velocity of light. Our relative permeability that we just discussed will be 1. Then the permeability of iron will be just vacuum permittivity. Frequency is 500 megahertz. And so then we already have the formula here for the reflection loss. So if I go back to our lecture slides, this is what we had done last time. Oh, unfortunately, I've closed the lecture slides. So here they are back again. And so what we discussed, this was the approximative formula for the numerical value of the reflection loss in the far field. So this is the same formula that we also have here at this position in Octave. And we also developed a similar formula for the attenuation loss, or for the absorption loss. And this was this formula here. So we already have the formulas. We need to have the thickness. And the thickness, according to the task sheet, is 0.6 millimeter. So 0.6 and milli is 10 to the power of minus 3. And so this should be the approximative calculation. And so here I think I just need to change all the values from aluminum into iron and from aluminum into iron from the previous calculation. And right, then we calculate wave impedance in metal, wave impedance in air. From this we calculate these transmission coefficients as in the task before, our propagation constant, the reflection coefficient, and then the exact shielding attenuation. And so let's just run this and take a look at the result. And I need to, I think, comment all this stuff here in so that we see the results. And the total one and then the exact result. Okay, and so we get some reflection loss that is not super high, but of course as the wall is quite thick in comparison with our skin depth, because skin depth is just some micrometers at 500 megahertz of frequency, we get super high attenuation due to absorption. And as this absorption is larger than 10 dB, we don't need to take into account the multiple reflections. And we get 820 dB from the approximative solution and also from the exact solution. Okay, so result here with these values is that we get a total shielding efficiency of approximately 820 dB. So how would you discuss this? If someone has made a shield and tells you, my shield has a shielding efficiency of 800 dB.
It's very impressive.
It's very impressive, it's super high. And of course it's the case for this case if we would have a perfect metallic wall all around, and if we would weld it together, let's say. If there would no cables go in, no cables go out, but the practical computer case, of course, has many cables going through. You need to have ventilation holes, you need to have openings for buttons, you need to have openings, I don't know, for some, or at least in former times, for some compact disk drive, something like this. So the real shielding efficiency will be smaller. And this is also already what we have discussed now here in task B. So what is the limiting factor for this? And I think I can also type text here. So we could say it's apertures for ventilation, for example, and for buttons, openings for e.g. disk drive, cable feed-throughs, and yeah, what else? Do you have other ideas? So for the computer case, of course, you sometimes want to open the computer case to put something or to build in components, new components to replace some components. And a computer case never has these, if I switch to the document camera, right, you don't see something like this in a computer case. There's just a metal to metal contact, maybe with some screws. So the case itself, or parts of the case to be opened, or the contact between parts of the case to be opened is not perfect. And this will, for example, also lower shielding efficiency or shielding effectiveness. Can I make this font a little larger? Oh, now it's even getting smaller. Now it's gone. No! I don't know how I can... I wanted to increase the font size, but I made it smaller. Here I can format the text. And let's make this a little larger. Okay. Okay, then next task is a quick discussion on how could the shielding efficiency or effectiveness be measured. So we have this computer case. In practice, we have built it, and so we would like to measure shielding efficiency. What would you suggest, or what would you propose to do this? So what would be a reasonable measurement setup?
Like be in a semi-anechoic?
We could probably do it in a semi-anechoic chamber. I would say we not necessarily need to, but of course, it would certainly not be a bad idea. So let's say we have some big shielded room to shield us from the surrounding, and so we don't want the inner walls to be reflecting. So we have absorbers on all sides, or at least on the walls, right? So we have lots of absorbers here and lots of absorbers on the other wall, but not on the ground, because then we cannot walk around into this chamber. So absorbers here and also absorbers on the ceiling. Okay, so we have made an SAC, a semi-anechoic chamber. Okay, so what would be next?
We need that to generate that disturbance signal?
We need to generate some field on the outside. So we take some antenna, for example, and I will draw a logarithmic periodic dipole antenna that could be used for this frequency of a couple of 10 to 100 megahertz to some gigahertz. If we would go for higher frequencies, we could also use a horn antenna to generate field. And so I don't know if this is a nice schematic for some horn antenna, maybe. And so if we go for lower frequencies, if we would like to measure shielding efficiency in the kilohertz range, what would you suggest there?
It's the antenna with a multiple dipole.
Yeah, or just a loop antenna. So we would like to have some antenna that can be fed by a current to create the magnetic field. So at low frequencies we would use a loop antenna, right? And let's say this would be in the kilohertz range, this would be in the megahertz range, very simplified. And the horn antenna is what we would use in the kilohertz range. Okay, so we have some antenna to generate a field. So how to continue to measure shielding efficiency? So we would need to have our shielding enclosure. And so to measure this computer case would already, with a kind of setup like this, quite complicated because a usual large, big logarithmic periodic dipole antenna would not fit in there. But of course we can have a smaller antenna that somehow works like this. So now we take our computer case, our shielded enclosure, and we also need to have some antenna, some field probe in there to measure the field in there. So I will draw a small antenna in there. Okay, so we have some antenna on the outside, we have some antenna on the inside. And what do we do now? So it would be good to measure the coupling between the antennas with the case, with the shielding case, with the shielding enclosure and without the shielding enclosure. So we measure the coupling between the antennas, and what would be a good instrument to measure coupling between two antennas? Or to measure transmission between two antennas? Or to measure also what might be, if I generate a signal, if the antenna is not perfectly matched, what might be reflected, directly reflected back at the antenna and not even transmitted, and so on. And so the general term for transmission and reflection would be scattering parameters. So with which instrument we can measure scattering parameters very easily as a function of frequency? With some network analyzer, vector network analyzer. So we take a VNA and say with this VNA vector network analyzer, we transmit a signal that is called A1 at port 1, and there is some signal reflected back, B1, and so we have a second port, and also at the second port we might transmit a signal A1 and no, A2 of course, and we might get a signal back that is called B2, and from these transmitted and reflected waves we can calculate scattering parameters, and the scattering parameters would be defined in this way that the reflected waves B1 and B2 we get from the transmitted waves A1 and A2 via these four scattering parameters S11, S12, S21, S22, and the elements on the main diagonal, this would be the reflection coefficients, right? What is sent at the port and what is reflected at the very same port, and what is sent in port 2 and reflected at port 2, and the off diagonal elements are the transmission coefficients. So what is sent at port 2 and received at port 1, or what is sent at port 1 and received at port 2. So our interesting component, let's say now for the shielding, would be S21, for example, because this is what we send here and what we receive inside the shield. But as long as our whole system is linear, it should also work the other way around. So we could also transmit a signal into the shield and look what we receive on the outside, or what we could send on the outside, see what we receive on the inside. So for a passive linear system, these two off-diagonal elements should be equal. Okay, and so we do this S21 measurement without the shield, measure the coupling between the antennas, then we add the shield, and then we can take the ratio between the two will be the shielding efficiency, and ratio on a dB scale is the difference in dB. So let's say our shielding attenuation here that we just calculated would be the S. I don't like to write it this way. I would rather write it's the level of the S21. Right, this is in dB. Now it's a question if we have, so this would be, I think, without the shield. No, good question. So here at the end we want to get something positive, right? Because shielding efficiency should be positive. So we need to have a larger number minus a smaller number. So I think our coupling, we need to have the larger coupling minus the smaller coupling. So this should be without the shield, or let's say, I don't know, the direct path, and this is the shielded path. So I would say this is without shield, where we get a good transmission between the antennas, and this is with the shield where we get a smaller transmission between the antennas. And this is one way how you could do it. We assume that the reflection at the antennas is the same for both cases, so we would just measure this S21 and then the difference between the two, and this should be that should be it. Okay, so this would be one way to measure shielding efficiency. Take two antennas, measure the coupling between them, with and without the shield, take the ratio or take the difference in dB, right? So this equation here is, this is with levels in dB, or with, rather with gains and not levels. But in decibel scale, let's say. Okay, so then we can come to the last question. What problems might occur at higher frequencies during this measurement, and from which frequencies would you expect such problems, and how can they be solved? And yeah?
It's referred like to the aperture like of the case?
Yeah, it's meant to be what is the problem of this measurement itself. Of course, if the shield would be perfect, I mean, we would have this 80 to 820 dB, so we would not measure anything. But due to all the imperfections that we discussed, the shielding efficiency or effectiveness will be much lower, will be, I don't know, 40 dB, 60 dB, something like this. So something that we could measure, because these vector network analyzers, they have a quite high dynamic range. So they have a dynamic range, let's say in the order of 100 dB, maybe 120 dB, depending on frequency. So if our shielding is lower than the dynamic range of this instrument, we would be able to measure it. And let's say, yeah, let's say we have enough dynamic range here, so we can measure it. Still, this proposed measurement setup yeah, might give us strange results, especially at higher frequencies. Higher frequencies means the higher the frequency, the smaller the wavelengths, if we have small wavelengths. So what will happen if we have small wavelengths? Wavelengths that are small in comparison with the size of our enclosure here. And so what happens if I go to a new page is, if we take a look at our shielding computer case, at our shielding enclosure, I will try to draw it a little bit. So this is the front side, and let's now try to make a little bit three-dimensional view. So this is all made out of steel, and then we might have some apertures, some openings somewhere where field can couple in. So for example, we have some slot here on the front side for some display or whatnot, and some field can couple in here. And here, so on the outside would be our field generating antenna, and this now creates some field, and this field will couple into this enclosure. And so the field will enter here through this aperture, and then what will happen? So the field will propagate through our shielded enclosure and will hit this metallic wall. And what will happen? It will be reflected back, and it will hit this wall, and it will be once again reflected back. And we have signals going back and forth. And so we might get standing waves. And the simplest standing wave, or the largest standing wave that we could get, is a one that has 0 at the wall, of course, and a 0 at the other wall, and that has the maximum in the center. This would be the first cavity resonator dominant mode that we can get. And a next mode would be, for example, we have a standing wave that looks like this. So if I just look at the magnitude, magnitude at the wall must be 0, magnitude at the other wall must be 0, but we have two antinodes of this standing wave and one node at the center. This would be half of the wavelengths, double the frequency. And so another mode would be, if I take another color, would be this one, where we divide this into 3 parts. And so we have one antinode, and another antinode, and a standing wave pattern that would look like this. And so then, right, the last one, I will maybe use black for this, is where we split this into 4 parts. So this would then look something like this. So we have one antinode, one antinode, one antinode, and another antinode, 4 antinodes connecting these 3 nodes of our standing wave pattern. And going back to the question, what is now the problem? What is the problem if we do the measurement like this?
We directly measure this?
So imagine we have our antenna on the outside, and now we are measuring the field on the inside. And now it depends on where we do the measurement. If we do the measurement, let's say at this position, then at this particular frequency we will measure a high field strength. At the next frequency we will measure a very small field strength. Even if there's a field inside the cavity, we do the measurement at the node, so we don't measure anything. At the next frequency, the gray one, we will once again measure something, and at the next frequency, the black one, we again won't measure anything. So now if we would plot the shielding efficiency or the shielding effectiveness in terms of frequency, we would, so this is frequency and this is our shielding attenuation or shielding efficiency, shielding effectiveness. So usually we would expect, and maybe before we draw this, maybe we can go back to our octave calculation and check how this would change. Now we have just calculated this for a single frequency, but we could extend this and do it for a frequency range. And so for our computer case, what might be interesting, for example, is to do it linearly spaced, or we could maybe also do it logarithmically spaced from maybe 100 kilohertz. Or we could even go down to 10 kilohertz. So let's say from 10 kilohertz to, what would you suggest as an upper frequency? 1 gigahertz, but modern computers are also working in the upper gigahertz. So maybe let's go to 10 gigahertz. 10 to the power of 9. And yeah, 100 points or so, the standard setting should be enough. And so now we just need to recheck our formulas here. So this is now a vector, of course. So this is a vector. This is also a vector. This should fit. This is also a vector. This should fit. But here it's getting complicated. We need to divide by a vector because this is now a vector. Here we also need to divide element-wise by this vector. This should be some scalar value. I think here we also need to do this division element-wise. Here the same, and probably also here at this part, at this part, at this, finally at this power, and probably also here. And okay, if there will be some error or mistake in the script, Octave will tell us, but it did some calculation. And of course now, okay, we get 50 values. So maybe we extend this to 500 values to have a smoother plot, and I will escape the results so that we don't have all the values on the command prompt. Okay, so let's run it again. So successfully finished, did something, and now we could plot. We could plot as a function of frequency. We could plot the 20 times log. Oh no, it's already in dB, right? It's already converted, so we can calculate this, and as a function of frequency we can also calculate or plot this one here. So we have the approximative solution and the exact solution. And we have not always checked that this A here is larger than 10 dB. So what we might also do is just plot the reflection loss and the absorption loss separately. Okay, and so we do this as a function of frequency. So here on this axis we have the frequency in hertz, and on the y-axis we have our shielding effectiveness in decibel. And let's add a legend, because we have already 4 curves and it might be confusing. I also don't know all the colors. So the first one is reflection loss. The second is absorption loss. The third is, let's say, the approximative solution. And the last one is the exact solution. Okay, and maybe a grid would be nice. So let's see what it does. Okay, does not look too bad. So let's make this a little larger. So the blue curve is the reflection loss, and we can see this is somehow going down with frequency, as we've discussed. Maybe it would be nicer to change the plot into semi-log x plot to also scale the frequency logarithmically. So let's run this again. Okay, so we can see that the reflection loss goes down with frequency, something that we discussed before. So then the absorption loss grows, and then the exact and the approximative solution are very close to each other. So we just see more or less one curve, and we can see how this shielding effectiveness increases with frequency. Okay, yeah, and so then we would expect that after some certain frequency, so here this is 10 to the power of 4, this is our 10 kilohertz, 100 kilohertz, this would be 1 megahertz, 10 megahertz, 100 megahertz, 1 gigahertz, 10 gigahertz. So starting from here, at let's say 10 megahertz, we have 30 meter of wavelengths. So that wavelength is getting small enough so that fields can go through some apertures and so on in our shielding enclosure. So if we take a look, so for low frequencies, okay, we have not so good shielding efficiency, but then shielding efficiency increases and we might reach some kind of maximum, but then we get this aperture coupling and shielding efficiency goes down once again, yeah, or reaches some plateau and does something. Maybe goes down once again because we have more coupling through apertures. So this is what we would expect, or this is what our measurement would tell us, should tell us. But if we do the measurement like this, at this antenna position here, what will happen is that, okay, at low frequencies it's the same, then it increases, okay, it's the same, then we have this aperture coupling, okay, it's the same. But now we are measuring at this particular position here at some frequency where we have this green wavelengths. So let's mark some frequencies. The lowest frequency was the blue one. The next frequency was the green one, then we had the gray one, and then we had the black one finally. And so now what would happen is that at the green frequency, if we are measuring at this position, we don't see any field on the inside. So it looks like our shielding efficiency is super high, but it is not really. It's just some effect of the measurement. So we would see, okay, here our shielding efficiency grows super high because we don't measure anything here, just noise. But at the next frequency, at the gray frequency, it's small once again. So there we measure something, but at the next frequency, at the black frequency, once again, we don't have any field. So there we measure some high shielding efficiency, and then it's going down once again. And this would somehow repeat, go up, go down, go up, go down, do something like this. And so what's the bad effect?
Not precise.
It's not precise anymore. We get some measured shielding attenuation that is not our real shielding attenuation, that shows artifacts of the measurement position. So now, okay, now we could change the antenna and maybe shift the antenna to this position here, for example. Yeah, and so at this position, okay, at the low frequencies, nothing would change, shielding attenuation would increase, we reach this maximum, and we get some coupling, yeah, and so here it would still be okay. At the green frequency, it would also still be okay, but at this gray frequency, for example, we measure less, and especially at the black frequency, we measure less. So it, yeah, I don't know, might look something like this, that we reach some maximum here, and then it would also continue to do something like this. And so changing the antenna position just shifts this problem to a different frequency. Still, our shielding attenuation depends on the measurement position. And this is definitely a problem if you measure shielding efficiency of such enclosures. So one solution would be, or I mean, now we could, as the task suggests, how can such problems be solved? How can we avoid such problems? What would you suggest? Yeah, so at least what we can do is measure multiple antenna positions on the inside. So, other ideas? I mean, one problem is that we have this reflection here at the end. Or the reflection here, if we would not have the reflection, we also would not get a standing wave pattern. So what we could do is avoid the reflection by adding some absorbers or some absorbing material inside the shielded enclosure. And in practice, so if you have the computer case and if there will be some components mounted in the computer, like the main board, the motherboard of the computer, hard disk drive, cables and so on, there will be lots of absorbing material. Yeah, there will be lots of absorbing stuff inside the computer case. like cables, PCBs, other components, and so on. And they might all absorb electromagnetic waves. They will change the field pattern inside this enclosure. You will get this different standing wave pattern. Still, you might get a standing wave pattern. If you don't know what's happening inside this enclosure, what the quality factor and so on will be, it's difficult to tell what will happen. Okay, so this is somehow, once again, somehow shifted here. And other ideas, what to do? Instead of moving the antenna around inside our shielded enclosure, what we could also do?
Place more than one inside?
We could use more than one antenna, use multiple antennas, but this of course complicates the measurement, or a MIMO approach, right? Something with multiple input, multiple output. And the other thing that we could do is we could try to turn our small shielded enclosure into something like a small reverberation chamber. We can try to leave the antenna at one position and move this standing wave pattern inside, around inside this room. So we can use a mode stirrer inside the small enclosure or inside the shielded enclosure, like in a small reverberation chamber. And yeah, this would be also some idea to get rid of this artifact in the measurement that we sometimes see a very small and a very high shielding attenuation due to imperfections or due to the standing wave pattern of the field. And okay, there might be some other ideas, but I think these are the main ones to be discussed here. So last question that we can probably solve or discuss is, from which frequencies would you expect such problems? And how could we calculate this corresponding frequency?
But for discussion, should we like suppose a dimension for this aperture?
It's more about the dimensions of the case, because of course the aperture, this will be the cause for the coupling from the outside to the inside, but it could be also a cable, it could be some other kind of feed through, some ventilation hole, but this standing wave pattern on the inside, this just depends on the dimensions of the enclosure. And so these dimensions are given here. And now the question is, how could we from these dimensions calculate the resonant frequencies, because this would be the resonant frequencies of the resonant modes inside this cavity, inside this shielding enclosure. So how could we calculate them?
So it's when the wavelength dimension is less or equal to...
Exactly, when the wavelength fits to the dimensions of this chamber. And there is some formula to calculate this, and this formula I think we also somewhere find on the Wikipedia page. So if we check for cavity resonator, and there's also some cavity resonator calculator that we might use from the Learn EMC website, but this is what we can use later on. At first we will just check Wikipedia for cavity resonator, and there hopefully should be some page, not really, resonant cavity. This does not look too bad. So transmission line resonators, mechanical cavity resonators, cavity magnetron. It's not really the formula already that I'm looking for. So no, it's not a magnetron. I'm not sure if the waveguide formula will help us or if there is some formula here to calculate this. Also not really. So then we can of course check if there is, if we search for reverberation chamber, because this also belongs to the theory of reverb chambers. And there we need to look for electromagnetic reverberation chamber, and here we find the picture of the chamber in Magdeburg, and there is some general statistics, and here is the theory for the cavity resonator. Okay, so the eigenfrequencies, natural frequencies, resonance frequencies of some cavity resonator can be calculated by this formula. And here we have velocity of light divided by 2, and then L, W and H are the dimensions of the cavity, length, height and so on, and M, N and P are non-negative integers, and only one of them can be 0. And so if we set this to the largest dimension, this to the next smaller dimension, and this to the smallest dimension, and this to 1 and this to 1, then we should get the smallest frequency, the first resonant frequency of the cavity. So let's use this formula and go back to the drawing program. Okay, and paste this. And the corresponding calculation I will of course do in Octave. So we can try to use this formula and say the resonant frequencies will be C divided by 2, and I think C is what we have calculated before, but we called it C0, C0. And now this multiplied with the square root of M divided by L squared, and now I will copy this, plus N divided by W squared plus P divided by H squared, and the square root of this term. And now if we set M to 1 and N to 1 and P to 0, this should give us the smallest resonant frequency, and now we need to have the dimensions of the case, and this is what we find in the task sheet. So let's set L, the length, to the largest dimension, 305 millimeter. W, the width, to the next smaller dimension, 244 millimeter, and how was it called? H, the height of the smallest dimension, 190 millimeter. And so now if we calculate this resonant frequency, we can check the units in a second. We get this one. So if I convert this into megahertz, for example, by dividing by 10 to the power of 6, we get 700 something megahertz. And so we can check the unit here of our frequency and say the unit of the frequency is the unit of the velocity of light, which is meter divided by second, and something is wrong here. So meter divided by second, and then we always have something dimensionless. This index has no unit, but we divide by meter, square it, and then take the square root at the end. So we just divide by meter, right? And then this meter and meter will cancel each other. Yeah, and something is wrong here, but okay, you get the point, right?
Yeah.
Okay. So the unit that we get is 1/2, and 1/2 is the same as Hertz. So these frequencies, these resonant frequencies, the first one here where this is a problem, or where this might be a problem, is at around 700 megahertz. And so now you could insert different numbers for M and N and get different resonant frequencies where this might be a problem. Okay, so this is the relevant Wikipedia page here. Unfortunately, you cannot find it for the plain cavity resonator, but now we can take a look at the cavity resonance calculator from Learn EMC. And so here you can use this rectangular enclosure, and we can say it's the dimensions are 300, or can I change this to millimeter? Yes, I can. So 305, 244, and 190 millimeter, and relative permittivity is 1 because we have air, and now we can calculate, and then it will also calculate the very same first resonant frequency for the 110 mode that we also just calculated here in octave. So it's the same underlying formula, and I would expect if we would check the corresponding thing here, yeah, you can insert the mode numbers, some dielectric constant and magnetic permeability, and calculate. Question is if this is really the full epsilon and the full mu, or if this is the relative thing. So probably it's you need to insert the full values. So we can check 244, 190, 110, even if it says should not be 0, but we set it to 0. And let's say if we set this to 1 and 1, what do we get? Okay, we get the right thing. So this is just the relative dielectric constant, relative permeability in this case. Okay. Which questions do you have related to this task? Okay. So one last thing that we could do is ask ChatGPT, because this is a task that is maybe not too complicated. So now I need to go back to this text tool, I think, and copy this. No, this is not to copy, this is to write text. Yeah, so this is the right tool here to select text. And let's copy this, and there's ChatGPT, and we will message ChatGPT and ask, we have this computer case, we have these dimensions, what to do and what not. And so it calculates some skin depth. And the skin depth is something that we have calculated before. Steel's resistivity 10 to -7 ohm meters. I think, so if we go back and look at our script, I think this is also something that we used here, right? Around 100, 10 to the power of -9 is something like 10 to the power of -7. Okay, so this works. So it calculates us some skin depth. Square root of 10 to the power of -7 divided by this meters. I'm not sure, we got something So our delta, now of course difficult to say because we have changed the frequency to our frequency vector. So if I recalculate it just with the single frequency, our delta, where's my prompt? Where's this? Here it is. So delta was something like this. I would say square root of 10 to the power of minus 7, 1e minus 7 divided by 628. Naja, okay, we get something at least in the same order of magnitude, does not look too bad. So when we get some shielding efficiency, but it's not really calculating some value. But this would be the formula for just for the absorption loss. Okay, so limiting factor, joint seams, openings, discontinuities, gaps, imperfections. Okay, this is what we discussed. And for the measurement, it proposes by comparing the strength of some electromagnetic signal inside and outside the enclosure, or with and without the enclosure. We need to have a controlled source of electromagnetic waves, and we need to place a receiver inside the enclosure measuring the attenuation of the signal. Okay, not too bad. So then problems at higher frequencies, increased leakage and penetration. Okay, because this will limit the shielding efficiency, and then we have resonances inside the enclosure and limitations of material effectiveness. And okay, it says above 1 gigahertz, these problems or these resonances, these issues can be a problem. So we need to have tighter seams. We can put absorptive material inside the enclosure that we already also discussed, and we can try to do some additional calibration stuff like this, right? And this brings us back to what I had shown with the document camera, these shielding materials here, to get what is suggested here, a tighter gap. Where was it now? I think I've closed the tab. Okay. So this, I think, is a quite good and nice solution and summary of this exercise task about shielding and the practical implications associated with it in the measurement and what happens in the real life.